All right, if you're deep in university-level calculus, you've definitely met vectors. Those arrows with both a direction and a length. But have you ever stopped to think about how you actually multiply them? Yeah, it's not as simple as it sounds. Today, we're going to build your complete toolkit for one of the most powerful tools in all of vector math, the dot product. Let's get right into it. You see, multiplying a vector by a plain old number, a scalar, that's easy. It just stretches it or shrinks it. But what happens when you try to multiply a vector by another vector? Now that's a puzzle. We need a special kind of tool, one that can unlock the geometric story happening between them. And that tool is the dot product, sometimes called the scalar product. The name kind of gives it away, right? It takes in two vectors, does a little magic, and spits out a single number, a scalar. And this number isn't just random. It's a super precise measurement of how much one vector is pointing in the same direction as the other. You could almost think of it as a parallelness score. So, here's our game plan. We'll kick things off with the two main formulas. Think of them as the schematics for our tool. Then, we're going to put that tool to work on three key jobs. First, a quick test to see if vectors are at a right angle, then finding the exact angle between any two vectors, and finally, casting a vector's shadow using something called projection. Okay, first things first, let's pop the hood and see how this thing actually works. There are two main ways to calculate the dot product, and the one you pick really just depends on what information you've got handy. So on the left, you've got the algebraic definition. This is your absolute best friend when you have the components of the vectors. You just multiply the matching parts, the x's, the y's, the z's, and add them all up. Easy. Then on the right, we've got the geometric definition. This one's perfect for when you know the lengths or magnitudes of the vectors and the angle between them. Both formulas get you to the exact same place, that single scalar number. All right, tool in hand, let's get to our first job. How can you tell if two vectors are at a perfect 90-degree angle to each other? In vector speak, we call this being orthogonal. And believe it or not, the dot product gives us a shockingly simple way to test this. Let's take a look at these two vectors, A and B. Just by glancing at their components, could you tell if they're perpendicular? It's not obvious, right? So let's fire up our algebraic formula and see what it tells us. We're just going to follow the recipe. First, multiply the corresponding components. So 2 times 3, 4 times -1, and -1 times 2. That simplifies down to 6, -4, and -2. Now for the last part, we just add it all together. And what do we get? 0. Now, in math, 0 is rarely just 0. It's usually a giant flashing signpost pointing to some kind of special relationship. And here it is, the big takeaway. If the dot product of two non-zero vectors is 0, it means they are perfectly 100% orthogonal. It's that simple. It's a clean, foolproof test. Job 1 is done. Okay, but what if the dot product isn't 0? Well, that's when things get even more interesting. It means we can use it to find the exact angle between those two vectors. To do this, we'll need to grab our geometric formula and just rearrange it a little bit. Let's try it with a new pair of vectors. We've got A as 1, 2, 3, and B as 4, 0, -1. Our mission is to find that angle, theta, that sits between them. Okay, let's break this down. First up, we calculate the dot product the algebraic way, and that gives us 1. Next, we need the lengths or magnitudes of each vector, which turn out to be the square root of 14 and the square root of 17. Now we can plug all those numbers into our rearranged geometric formula. After we solve for theta, we find the angle is about 86.3 degrees. And this is where it all clicks into place. Look at that result. Our angle, 86.3 degrees, is really close to 90, and our dot product, 1, is really close to 0. See the connection? This is not a coincidence. It's the whole idea in action. The closer the dot product gets to 0, the closer the angle gets to 90 degrees. All right, on to our final and maybe my favorite job for the dot product, vector projection. The best way to think about this is to imagine a light source shining straight down from above. The projection is literally the shadow that one vector casts onto another. It tells us exactly how much of one vector's length lies in the direction of the other. But hey, before we dive into the formula, a quick but super important warning here. When you project vector B onto vector A, the final shadow vector you get will always be parallel to A. Getting A and B mixed up is one of the most common mistakes, so really pay attention to which vector you're projecting onto. So let's put it into practice. Our task is to find the shadow that vector B casts onto vector A. Now, the projection formula has a few parts, but they're all things we've seen before. The top part, the numerator, is just our good old dot product, which here is 7. The bottom, the denominator, is the magnitude squared of the vector we're projecting onto, so a in this case, which is 17. That gives us a scalar, a fraction, 7 over 17. And the very last step is to just multiply vector a by that scalar, which basically just resizes it. And there we have it. That's our final answer. That is the projection vector. You can see it points in the same direction as A, just like we said it would, but it's a bit shorter. It is literally the shadow of B on A. So, let's just do a quick recap. We've just added 3 incredibly useful tools to your vector toolkit. You now have a super fast test for right angles, a precise calculator for finding any angle, and a way to calculate a vector's shadow. And it all comes from one elegant, powerful operation. So now that you really get the mechanics behind a vector shadow, I want you to think about this. Where does this stuff actually show up? I mean, how do physicists calculate the work done by a force? How do video games create such realistic lighting and reflections? The answer, more often than not, involves the dot product. It's the invisible engine running behind so much of the world you see.